Yes, sure. Yeah, please, and then please ask questions in the middle of the talk. If the talk is kind of modular, I'm going to stop in the middle to get questions if the chair is okay with that. Thanks, Guillaume, for putting this together and company. And as anyone else, I'm frustrated that we could not come to Clermont-Ferrand. Donc, so I actually wanted to talk about more topological photonics and quantum topological photonics part, but it turns out that there is some problem, which I will tell you in the middle of the talk. So mostly I will talk about the theory, but let's just give a teaser of this topological photonics. So, okay, we know that these solutions of the Maxwell's equations, some of them are robust because of topological behavior. I was sleeping most of the previous session, so I'm pretty sure that you had enough of topological photonics. And this is a review that it's really meant for undergrads, and this is a more exhaustive review. And recently we have been looking at going beyond linear regime. So most of this review was about linear physics, and we have been recently looking at quantum and nonlinear properties of the topological photonic systems, in particular when they don't have an electronic equivalent. So one of the platforms that we have been looking into was this coupled ring resonators that we have been able to do like a imaging of the edge states, looking at spectral flows, doing something like a Haldane model, more recently higher order topological states, and other groups using ring resonator systems to look at the topological lasers that Jacopo talked about, and then even more recently using reconfigurable systems. So in that systems, we have been looking into whether we can generate pairs of photons in a robust fashion. So the way that you generate pairs of photons, sometimes you use this four-way mixing process. For the four-way mixing process to be efficient, you need to do energy and momentum conservation. So not only your energy of the pump should add up to the energy of the emitted photons, but also the momentums should match. So this is the incoming momentum of the photons, and these are the outcoming. But then, as you know, in a one-dimensional system, if I want to do it in an array, that because of disorder, the momentum is not a good quantum number anymore, and then you can have problems like this. So this is the joint spectral density of the emitted photons for one device and another device, and because of some on-site disorder, you may see variations from in this joint spectral density. So one is like this, one is the other thing. And this is just basically precursor of the Anderson localization. As we put more disorder, this is going to get worse. And we have been looking whether topological photonics can help with this problem. In particular, we know that transmission properties, linear transmission properties in these topological systems is robust, meaning that if you look at the transmission as a function of frequency, or if you look at the delay time as a function of frequency, and then do the experiment many times, and these different lines, different curves correspond to different devices, and then you superpose this spectra, you see that where the topology is expected, in particular in these edge bands, topological edge bands, then you see a suppression of the noise. So that kind of tells us the linear properties are robust, and then you can say, well, can we use this for nonlinear processing, specifically for phase matching? And in the past, we looked at generation of distinguishable photons, meaning that we pump the system, we generate signal on idler at two frequencies that add up to twice the frequency of the pump. In a 1D system, you see that it varies from device to device. So these are three typical devices. But in a topological system, you see that the emission is robust and it comes out in the same region. Despite the fact that we have strong disorder, and then also the magnetic field varies from site to site. This is the experimental result, and the numerical result shows us that this similarity as a function of the system size stays the same for a two-dimensional system, while for a one-dimensional system goes down with the increased fluctuation. This was for the distinguishable photons, which was done a couple of years ago. Now, recently, we looked at identical photons, indistinguishable photons, because that is useful for some of the applications, in particular, like boson samplings. And it would be nice if one can have many of these photons identical generated on chip. So instead of pumping here and then generating signal on idlers at two different frequencies, you do the reverse. You pump at these two frequencies, and in general signal either at the same frequency. So this is a recent paper that we put on the archive. So I was planning to talk about this, that the linear optics we understood, quantum regime we kind of understood, but the nonlinear part is even harder than the quantum part, I have to confess. With Sunil, we've been looking into this for a long time, and there are other groups that have been looking into these nonlinear properties, apart from the laser, just looking at solitons, etc. But finding a regime that things make sense has been very difficult. And recently, Sunil figured this out, and in particular found a regime where you can have combs. Unfortunately, it was just told last night that one cannot talk about this because we filed a patent on it. And usually I hate people when they say that, oh, we have done something and I cannot talk about it. But now this time I'm that person. So mea culpa, I'm very sad about it. So instead, I'll talk about some theory that it's related to the work that, for example, Patrick was talking about earlier. In order to set the stage, let me tell you how I see this field. So in quantum optics, you usually have two axes. You have the photon number and interaction strength per photon. So when the photon number is low and interaction strength is weak, you have linear optics. And then if you add many number of photons, then you have classical nonlinear optics. Now, if you increase the interaction, for example, by putting your atoms in a cavity that has support some specific modes, I was hoping that I would come to France and I would have some Magret Canard, but it did not happen. So then instead, then we get like the regime of cavity QED, that the photons and atoms strong interacting with each other. And if I have many of these photons now strongly interacting with each other, then I get, for example, a Mott insulator of photons, Laughlin state that Jacopo was talking about. I would like to add now another axis to this. Here, we were dealing with electrons that are weakly interacting with each other, or almost not. So like diamond centers, quantum dots, etc. But what if we add this axis? What if our electrons are strongly interacting with each other? For example, if they are in a fraction quantum Hall regime, or if they're a Mott insulator or a spin liquid, etc. So then my phase space would look like something like this. So this will be the interaction strength. This would be a photon number, and then now correlation, electron correlation. So this we kind of know very well. This is the exciton polariton. For example, topopolariton that Guillaume and company have been working on this would like fit over here. So the electrons again are weakly interacting each other. But if the electrons start to strongly interact with each other, then we can have, for example, this regime of cavity fractional quantum Hall effect. Or if we have just not use the cavity, just increase the number of photons, and while having strong correlation between electrons, we can have driven superconductivity, etc. If we don't have correlation, then we would be single particle physics and laser-driven systems. That would be like a full topological engineering. So this kind of is like an emerging field. And I've used this joke before, but I use it again. In contrast to this topological photonics that we knew what was going on, the microscopic theories and experiments don't really match. They want to get to this gold mine, but we're kind of missing each other. So it has to be taken with a grain of salt. The full idea is that basically, can we use light to engineer and control correlated electronic systems? So two kind of categories of models that we have looked into. These are all theoretical systems. One is using light to probe and manipulate topological states in two-dimensional systems. The other one is to use light in superconducting systems. Can we use light, for example, a cavity to enhance superconductivity? Can we use plasmons to enhance superconductivity by melting the competing order? Can you use the squeezed light to enhance further superconductivity? So these are the questions that we have been looking into. So in the first part, how we can use light to manipulate topological states of electronic systems. The motivation is that usually transport experiments are coherent, but global. We don't have a local information about this. STM and SET measurements are local, but they don't carry, usually they don't carry coherent measurements. So can we use light to do both at the same time, coherent and at the same time local information. So in order to do that, one can look at, I skip some preliminary points. The whole point of this slide is that if you couple electromagnetic field to graphene, so you do minimal coupling for graphene that starts with a linearly dispersive Hamiltonian, then instead of getting your Landau level that were equidistant for a quadratic system like quantum Hall and gallium arsenide, instead you get the square root independent. So as a function of magnetic field, these fields curve up like that. That's important because it gives you optical selectivity. So you can have you can actually distinguish which Landau levels you're coupling into from the conduction band to the valence band, vice versa. So people actually have done optical measurements, and then in particular in Grenoble, and then they see as a transmission you can identify these Landau level transitions. What we realized that it is not as simple as we thought. So just the dipole transmission and elements from one Landau level to another Landau level can describe this physics, but there is more to that. We know that these topological states are extended. So can dipole approximation be always valid or not? So as I said, dipole approximation considers when you have electronic cloud much smaller than the wavelength of light. So that's cool. But then what if my electron wave function is much bigger than the wavelength of light? So for example, in an extended state. So in a case of quantum Hall effect, you can think of a transition between Landau level 0 to Landau level 1 from one Landau orbit M, so this is in a symmetric gauge, and then to another Landau orbit M. So in the symmetric gauge, it would take this form. So the R is the radial coordinate, and then theta is the angle. And then I can write this A, the electromagnetic field, also in the cylindrical coordinate for convenience. So you get some bunch of Bessel functions, and then these states. So in the paraxial approximation, you just Laguerre Gaussian fields that have these vortices that carry orbital angular momentum. So now the manifestation of orbital angular momentum conservation would be that if you go from orbital M to orbital M prime, that can be satisfied as long as your light provides that extra angular momentum to the electron. So the angular momentum of light will be transferred to the electron, and then the final orbital angular momentum will be just the addition of the original angular momentum of the electron plus the angular momentum of light. So this is in principle possible, but whether this integral is large or not, we have to perform the radial part of this integral. And that's what Michael did a couple of years ago. And then what we realize is that this branching ratio, that how much of our emitted photon, let's say in a photoluminescence, is dumped into the orbital angular momentum, non-zero orbital angular momentum versus zero angular momentum, how much it changes. So naturally, if you go to a small system, that then you would definitely have dipole approximation. So the higher orbital angular momentum are suppressed. But then if you go to a large system, when your edge states, for example, is very large, then you can have emission in the higher orbital angular momentum. In particular, you can find what's the maximum orbital angular momentum that you can have. Can you do more? Can you actually use this orbital angular momentum to manipulate electronic states? Can you impart it? Like, can you do a Laughlin pump with OAM of light, the same way that Laughlin used the flux? Can you use now the OAM of light? And for that, I will invite you to look at a poster by Ben Cow. I hope that's in the system. So now that was just the linear part, the single particle physics. Can we do more? Can we use light to actually engineer the effective interaction in the photonic systems? So in particular, there are very interesting physics in a bilayer graphene. They have two layers, and these two layers are they have Coulomb interaction in each of them, and then in between them, then there are many interesting physics about that. Well, the question that we asked a couple of years ago, can we have a single layer of graphene, but instead we optically drive two transitions in between them? Can we have a synthetic bilayer system where now Landau level 0 and Landau level 1 play the role of two different layers? Of course, the Hilbert space is the same, so different Landau level indeed can play the role of different levels. Light can play the role of the tunneling, okay, so far so good. But the more interesting part is the interaction. Okay, so the Hilbert space is exactly the same, but what really makes it interesting is what happens to the interaction. In particular, we have a nasty interaction between different orbitals and different levels, and now we have to write it in a different in the right form. For the experts in the audience, when you have the rotational symmetry, you use Haldane pseudopotential. So when you have rotational symmetry, the interaction can be simplified just in the terms of the relative momentum. So for Coulomb interaction is something like this, that this is the relative momentum between two electrons, and then the strength of each channel, which would generically is just the monotonically decreasing. So if you do it for the synthetic system, then you have the like lower Landau level and upper Landau level. The electrons can have Coulomb interaction in the lower one. They can also have Coulomb interaction in the upper one. This will be like Coulomb interaction in the lower layer of bilayer graphene and the upper layer of bilayer graphene. They can also have Coulomb interaction in between, so interlayer like that. They can also have these terms that are not usually present in a bilayer system. So if you put all these together and you look at the Haldane pseudopotential, what you see is the following. For the inter-Landau level pseudopotential, instead of being monotonically decreasing, which was the case when if you optically couple 0 to 1 orbitals, then you see that it actually starts from a lower value and then it goes up and down. So what is happening is very simple. So I start with the Coulomb interaction. I cannot change the Coulomb interaction. That's the kind of nature given. But I make terms that optical drive would make some of these Coulomb interaction terms more relevant than the others. In particular, when you're bringing one layer resonant to the other one, then only those two layers are relevant in the Coulomb interaction. So if I just go to that subspace, the effective interaction would have a different form. So in a way, using light, using optical drive, we have been able to engineer the effective form of interaction. So this is very similar to the Fouquet topological insulator, where you use light to change the tunneling properties of the system. Here we are changing the effective interaction in the system. And then Zipe did recently more numerical simulation to show that one can stabilize some Fibonacci states like that. So this kind of effective interaction engineering will come later in the second part of the talk. Now, this was for topological system. Over there would be for superconducting systems. So now let's look at the superconducting systems. Can we use light or cavity physics to enhance superconductivity? But before that, if Guillaume allows, can we get any questions?
Yes, we can try. So are there any questions? Raise hands if you want to ask questions.
Okay, good.
Or maybe no, we are not yet ready. We have to find the button.
So it's tricky. Okay. Just you have to push the participants, and then in participants, there's a raise hand. So if there is no question, I'll continue. So then the second part, we would like to see whether light can actually enhance superconductivity. And we are not the first actually to look into this. This is a very, very old problem, like meaning that I have a superconductor, I put it in a microwave, whether it gets enhanced or not. And this goes back to 70s. People really looked into the system and then realized that you can enhance superconductivity. And the idea would be that you have a superconductor, you have a gap, and then you have this volume of quasi-particles. If you shine light with a frequency that is smaller than this gap, then you cannot evaporate these Cooper pairs. Instead, you can get rid of these Cooper pairs and then put them at some higher frequency and higher energy. And then that would enhance your superconductivity, because in the gap equation, the presence of this volume of particle at the gap, at the edge of the gap, is what lowers your gap energy. So can we use this cavity QED toolbox to do this problem? This is a collaboration with Victor Galitsky and company, my colleague at JQI. So the idea is very simple. You have a superconductor. You can couple it to phonon, and then through the gap equation you get your gap. But now we couple it to an auxiliary photon bath. And if this photon bath is lower in frequency, lower in temperature, sorry, imagine, for example, vacuum, then in principle, you're cooling down this Bogoliubov of quasi-particles. In particular, in this gap equation, if you lower this, the number of these guys over here, then you effectively enhance this gap. In order to do that, one has to write a light-matter coupling. So you have your light in the cavity that is quantized, like similar to an exciton polariton system, and your J is just the current. But now, since it's a superconductor, you have to write it in terms of Bogoliubov of quasi-particles, so it's just a rotation. And you have a bunch of terms. Some of them are resonant, some of them are off-resonant. And then if you properly put them together, you have 4 different processes. One process is that you scatter a quasi-particle and then lower your energy. That's bad because you increase the number of quasi-particles over here. The other one, you can evaporate them. This is a good one. Another one is that you can actually condense, go and form a Cooper pair, and the other one is that you can evaporate. So the blue one is bad, and the purple one is bad because we are getting rid of our pairs, and the red one is good, and the green one is good. And then you can do this and then enhance the gap depending on the temperature of the cavity and depending on the frequency of your resonator. So that picture of cooling that I presented in previous slide is not exactly accurate as usual. One has to look at different processes. And in some situations, you see that it enhances even a cool resonator cavity can enhance it, but if the frequency is not at the right regime, it can actually decrease your gap. So this is a competition between these 4 processes. So that was the story of an empty cavity. But what about we parametrically drive our cavity? So that was like a thermal or a vacuum. What's going to happen to this? Does squeezing enhance mediated interaction? And that has been looked into for spins. But there are some subtleties that was kind of not completely looked into. So if I have a bunch of spins in an empty cavity, so we have you have a cavity, you have the spins that are coupled to the cavity mode, and then this is your basically Jaynes-Cummings coupling. Now, if you see that my atoms are coupled to this specific quadrature of light, so if I artificially enhance this,
you have 3 minutes, Mohammad.
3 minutes, okay. Enhance this, then I can increase the strength of my coupling. So in particular, if I squeeze this quadrature, then when I integrate out my photon light, then I would get an enhanced coupling. But what is important is that this enhanced coupling is phase sensitive. When you are talking about squeezing, you have to say squeezing with respect to what quadrature, and this quadrature is defined with respect to local oscillator. So one of them would be enhanced, the other one would be actually inhibited. So that was the case for the spins. A similar situation can happen for electrons in 2D. And again, with Victor and Andre, we looked into how can we use squeezing to enhance superconductivity. Like this is like optical direct squeezing in contrast to using phonons as auxiliary. So this is the linear drive, and this is the parametric drive. Then we see that for a regime, in increasing this, using some squeezing will enhance our RTC. So with that, I would like to finish. I'll skip the rest of the talk, and I leave you with the summary. So we looked into ways how we can use light to manipulate and sometimes engineer tunneling. This was the case of the tunneling that I did not talk about. and sometimes the effective interaction. And then over here, can we use like cavity physics and also light induced or enhanced superconductivity? Again, this I did not talk about. This was using plasmonics to kill competing modes, in particular charge density modes in cuprates using light. So with that, thank you for your attention. And if you're interested, we have also postdoctoral and PhD positions, so please apply. Thank you.
Okay, thank you very much, Mohammad, for the very nice talk. Now it's time for questions. So please. Okay, so yes, one question by Dima Solnishkov. Okay.
Well, actually, yes. In fact, I had the question for the first part, but I decided not to. Can you please come back to this synthetic bilayer? And I just probably missed the point. Or what do you mean by this synthetic bilayer story? It's
synthetic?
Yes, synthetic bilayer something. Well, I just didn't manage to understand synthetic bilayer what? Graphene or I don't know.
Synthetic delay.
No.
Age.
Bilayer. No. It was just in the end of the first part where you were speaking about interaction potentials. But okay, I understand that interaction potential is important, but what was the system in question? A little bit later.
This one?
Yes. So it was, okay, I understand what is bilayer graphene, but here it was synthetic or not? What do you mean by synthetic?
So let me that maybe was too quick. So in a bilayer system, I have two layers, two monolayers of graphene. Now, yes. What I'm saying is that imagine that I have a single layer. But in the single layer, I optically drive two Landau levels. Can this play a role of a bilayer system? So that's why I call it a synthetic bilayer graphene. So it's in a monolayer of graphene, but since I couple two Landau levels, can I think of this Landau level as one layer and the other one Landau level as another layer?
Okay, well, thank you very much. Now it's much clearer. Yeah.
So now you see that the Hilbert space in a bilayer system, we usually ignore all the higher Landau levels because actually we cannot calculate things. You should not, especially in graphene, you cannot ignore higher Landau levels. Landau mixing is important. But anyways, we ignore them. But here I'm resonantly driving to Landau levels. So now my subspace will be these two Landau levels, which would be the same as big as two Landau levels of two different layers, two physically different layers.
Okay, yes, I have a question from Walid Rejem. Please, Walid.
Hi, can you hear me?
Yeah.
Yes.
Yeah, so basically here in your system, you're applying an electric field to have the square root behavior, right?
Magnetic field.
Not an electric field?
No.
Because if you don't have an electric field, how you can have the different separation between levels?
Over here you're talking about?
Because if you're just applying, you are talking about applying an electric field, right?
No, magnetic field.
Okay. I think it was before, the slide before.
Quantum Hall physics. So in quantum Hall, one applies usually a perpendicular magnetic field. And then if you start with a system that has quadratic dispersion, you get Landau levels that are equidistant.
Okay. You start
with the linear dispersion, then you get this square root dependence.
Okay. This is great. Okay, thank you.
Okay, so are there any other questions? So no. So let us thank Mohammad again, and